engineers and all that kind of stuff. Like they'll gladly interview you if you can set up that situation. It's and more and more people are. But I see it now for sure. Like we're live, by the way. I see with people they show up at the exact moment of the interview now. Like everybody's so trained in this new world. It's a totally different experience now. I have a sign that I have to teach people how to use Zoom, and I don't need it anymore because everybody knows how to use Zoom and show up at the right moment.
I was 1 minute early. I thought I was. Yeah,
No, that was good. Minute. That was good. I was counting on it. I knew it was going to all come together.
Yeah.
Awesome. All right. So I guess we should do the interview portion of this. So who are you? What do you do?
So my name is Lee Cronin. I guess officially I'm the Regius Professor of Chemistry at the University of Glasgow. So to get this term Regius, it's a term given by the monarch. So it's the oldest Regius chair in chemistry, and I think it was done in first awarded in 1817 by King George, the same King George that lost America.
So if the Queen needs a chemist, you're at the top of the list. You're always on call if the Queen needs a chemist.
Sadly or gladly, no, that doesn't seem to be the case. It's mainly symbolic title, but it's a nice one. I have a letter signed by her and the Prime Minister of Scotland and so on. But yeah, I'm a chemist in Glasgow in the School of Chemistry. But really, I'm more of I describe myself nowadays as an experimental theoretician. I'm not smart enough to do theory, so instead I kind of do experiments that I don't know the answer to.
Right.
And then I basically then try and work out why.
Right.
Which I think is like how science is supposed to be, but it's tricky, and that's where I do a lot of my stuff. And the medium I work in is chemistry, but increasingly I do a lot of computer science and physics, and I'm a bit more confident on the side of looking at information theory and complexity.
So that idea of being what did you call it, a theorist? Chemist, is that right?
An experimental theoretician.
An experimental theoretician, because I love the balance between the experimenters and the theorists. How the theorists are sort of pushing the ideas, the boundaries of the ideas, but they have no idea if what they're suggesting is even possible. And on the other side, the experimenters try stuff, come with a whole bunch of weird stuff that's turned up, and then they turn to the theorists and go, what do you make of this? And the two are sort of really, if I had to choose, I think I like the experimenters better.
Yeah, I mean, I didn't choose per se. My educational upbringing chose it for me. I do a lot of my theory in my subconscious brain, or I lack the language to translate it to my conscious brain. Doesn't mean I'm not doing it. It just means I can't really tell you the working out.
Right.
But I can translate it into experiment, and I do tend to know what to do next.
That's
and I'm
neat.
Working with real theoreticians as well.
Yeah.
But it is kind of funny that a lot of the stuff we're doing just works. But I don't know. I only just worked it out in the last couple of years, right? And people say, you're a chemist in a chemistry department. Why are you doing fundamental mathematics, computer science, and physics? Yeah. I'm like, well, why not? And they're like, you're in a chemistry department.
Right. Like, sure. Get with those beakers, mix up some plastics, get back to work. Yeah.
Yeah, I mean, I do a lot of chemistry. I've got some brilliant chemists in the group, and they're doing really good science. But I think that chemistry is the medium through which we are able to kind of understand the emergence of life and information and consciousness and all the complexity in the universe. And physics is a really bit boring. I mean, physicists are know-it-alls. They're like, oh, yeah, we know the standard model. We know how this works. I'm like, they don't actually. But it's kind of interesting how physicists more for me are we know everything. And we're just going to pretend we're confused occasionally so we can get some research funding.
Right. Well, I mean, there is this sort of natural hierarchy of things, right? First you get the physicists, then the chemists, then the biologists is sort of the pecking order, I believe, is it, as you get closer and closer to the fundamental laws of nature itself.
But what it'll be ironic that we're going to find out in the end that physics is really a higher order manifestation of chemistry. Sorry, biology is a higher order manifestation of chemistry than physics, in that physics is like, biology is like just an extreme application of physics.
Right.
Okay. And what that means is that actually then by doing that, we suddenly realize And I was realizing this the other day, in the same way that the identity of matter in my body has been selected by some processes, the fundamental physical constants we think are unique are somehow connected in the universe are not that unique. And I think I can now understand the charge on an electron, the mass of electron is arbitrary. It's consistent in this universe because they all must have produced in the causal chain that gave rise to them. But there's nothing stopping an electron being any mass or any charge. It's just how it interplays with the other objects in that universe. But I think when physicists say that's a fundamental constant, you say, oh no, that's a fundamental missing piece of information you don't know. So when someone says constant, you're like, no, missing information. Should we insert God here?
Right. Yeah.
Insert God here.
Well, so I think you're sort of nicely queuing up then this idea of coming up with a toolkit for searching for life. So I'd love to sort of segue into your thoughts about sort of astrobiology in general and sort of how we move forward from here.
So astrobiology, I must admit, when people introduce themselves as astrobiologists, I'm a bit direct and a bit rude. So hopefully I don't offend you or anyone else listening. I was like, astrobiology, but that's a fake discipline because we haven't found any biology in space. And people are like, it's like, well, it is, right? What's an astrobiologist? It's like saying, I'm going to be an alienologist.
Right.
Like, yes. And they're like, yes, of course, that's what we are. We're alienologists. I'm like, oh, okay. And you're happy with that? Yeah, because there are aliens in the universe, we hope. And if there are, we're ready. I'm like, okay, fine. So astrobiology is a really interesting discipline because it is about getting people ready to even think about biology beyond Earth, which I think is worthwhile. I think there are traps with any new subject. I think astrobiology now reminds me about electricity before it was we really understood that electrons were doing this thing and we could accumulate them and we could build capacitors and we could build batteries and we knew what conductors and non-conductors were. They were right just at that so astrobiology and the origins of life people and the information theorists are all fighting to understand what is the description of the world which explains life. And astrobiologists saying, well, actually, let's go and find life elsewhere. That's a cool way to do it. So my thoughts on astrobiology are that it's a pre-paradigm discipline. We don't know what life is. So we don't know what life is. It's kind of hard to be an astrobiologist because you don't know what you're looking for. Right. But actually, those people who are brave to actually do that, I take my hat off to them and because they're trying to do something that's incredibly hard and they deserve our support and our being open-minded. So I think it's a really great discipline, despite my initial at the beginning when I was talking to astrobiologists, it's a fake discipline. It doesn't exist. And they're like, come on. It's like, and so I think that's good.
Yeah, I mean,
I think that...
Well, just that they have been able to push the search for life into some of the weirdest places. And maybe by describing it as such, they'd be able to get the funding to be able to drill boreholes kilometers deep, to be able to scrape goo off of nuclear reactors, to be able to collect particles from the upper cloud tops, to dig down into black smokers at the bottom of the ocean. That to even just be able to put a name on it and get prepared has allowed funding to be able to push even the boundaries of our understanding of life on Earth. I mean, I feel like in the last couple of decades, our even comprehension of what life is capable of has gone so far beyond what we thought just a few decades ago.
Yeah, I think that astrobiology has done a number of really important things. It has basically, first of all, really put in the center this notion that life shouldn't be confined to Earth and what does it look like? Where, why is it? Secondly, the fact that life on Earth is able to be found everywhere on Earth, even in the highest, driest deserts in the world, in the most pristine water, there's life everywhere. And also life seems to be resistant to that life is not necessarily just resistant, but it is able to work with the environment and indeed thrive in that. So I think understanding those, I completely agree with you. And I think it's also where we're at now is, whereas astrobiology and origin of life coming together, there's some kind of, not contradictions, but there's some problems because people are then saying, well, shall we define life? And shall we find the origin? And shall we do this? And then that's when the narrative becomes a little bit more representative of the interesting personalities that are conducting the science at the time, right? With electricity, there was obviously Tesla wandering around and Edison and a few other people. And so, it's this is the same right now. It's fascinating to watch.
Yeah, I guess that's interesting, right? That there are these sort of two tracks that people are going at it. One is, can we figure out how life itself formed here on Earth? And that will give us a clue on whether it's a common event, whether it's a very rare event. And then I guess the other possibility is, can we find it anywhere else, and then use that to sort of extrapolate back to how life formed here on Earth? Which, if you were to place your bets, which answer do you think we'll get first?
I think we'll get both answers, actually. But I genuinely think that I don't like the origin of life question, the way it's framed, because it's not falsifiable and therefore not scientific. It's a historical expedition. But I think that making life in the lab, which is what we're doing, so we're more about creating life in the lab rather than looking for life kind of historically, will be done. And I also think that looking for life elsewhere in the solar system is much more important than just. Do you want me to shut my window?
No, it's totally fine. Totally fine.
So I would say I'd rather look for life elsewhere, but I think trying to make life in the lab now might help me put boundary conditions on that. But the origin of life as a scientific endeavor, I think, is pretty on Earth. The origin of life on Earth is non-falsifiable and actually irrelevant. But that's not saying the same thing like understanding in general terms how the origin of life occurs on a rocky body is not relevant, and we shouldn't study Earth. That's great. So what I'm kind of saying is I'm trying to contrast two things. Let's say, right, Fraser, I'm going to tell you about how the sun started in our solar system. You'd be like, I don't care. Well, you might care, but
I'm one of the few people that might.
Much.
Yeah.
But you might say, oh, no, but I said to you, no, actually, I'm going to tell you how suns start, full stop. And you're like, now I'm listening because I understand general principles. And I think the problem is that we're in the origin of life. We are looking up, this is a simple thing, looking up into the sky, and all we see is the sun. We don't see any stars, and we're saying, how did that get there? We're just going to fix on that. And whereas we're ignoring all the stars.
Right.
And I think that we have to stop doing that. When we stop doing that and we start looking at all the stars, it becomes a statistical discipline, becomes falsifiable, and away we go.
Right. And astronomers do have other examples. And I think they have definitely been informed by watching star formation. In fact, they mainly use methods of star formation out there at various stages across the universe as a way to try to figure out what stage our sun went through. Without those other solar nebulae, we would pretty much have almost no way to really know where the sun came from. But this comes back to this awful problem, which is that we have no other examples of life that aren't on Earth.
Yeah, I mean, I realized something today, that actually life isn't the interesting thing. It's actually, there's something else that's far more common than life, that really all life needs, and that's selection, and how we see selection going on in the universe. I think life is the natural consequence of selection. And I don't mean biological selection, I mean selection before biology. All biology is a vehicle for speeding up selection. Biology is actually irrelevant. What biology can do, though, is it speeds up selection dramatically, and you can terraform planets and build the internet and make beams and all that good stuff, right? But actually, I'm realizing more and more we're asking the wrong question. We're fixating on an artifact which is actually not that interesting. We really should be asking ourselves, it's a bit like we're focusing on how I'm trying to think. For me, selection is like so the gravity of biology is selection. Like gravity, the gravity in the universe controls universe at long scales. It's almost like we focus on accretion and one object and say, oh, how's that stuff get together? And ignoring the fact there is this phenomenon called gravity. So again, we're looking at life on Earth and going, how does life on Earth work? We can see selection, but we're ignoring it. And we're just focusing on the end product, on one particular thing. And if you only look at one particular thing, there's only ever going to be n plus one of that. N equals one of that.
I mean, I think physicists have a similar idea when they sort of consider the universe, that really everything is driven by gravity. That if you start from the early universe and push time forward, every structure that forms, every star that forms, every planet that forms, every element that forms really are all consequences of gravity working in exactly the same way across the entire universe. Just where things started out defines where they end up and in what form. You know, if they start out as this cloud of hydrogen, helium, and end up as a beaver, it's just about the gravity that told the story. So,
well, yeah,
go ahead.
I would argue a little bit with that, but I know what you're saying.
Yeah. So then I'm sort of imagining, you're talking about selection, and so if whenever life formed, it picks up the story of the selection and applies the Darwinian selection as the evolutionary pressure, what was providing the selection before that?
Yeah, and so I think it's obvious and also very difficult. It's very difficult for physicists to get to grips with this because physicists are gods looking down on the causal chain, and there's got some fakes in there for us, right? And I'm going to say some heretical stuff today, but why not? It's Monday after all.
Yeah, there's nobody watches this thing anyway, so don't worry about it.
So I would say that our notion of time is kind of in physics has kind of got a bit the wrong way around. We have to add in things, fixes, second law, entropy, order at the beginning. If we made time a thing before space, we actually don't need entropy because time is always increasing, right? It's entropy is like, oh, there's this thing called time, but we're not allowed to say it's fundamental. It's like, okay, well, let's just assume time is fundamental because events are happening. That's the first point. So when you've got events happening and matter is moving around in that chain of events, then you have a number of things that can come from that. That matter will interact. Some structures will be made and some structures will be erased. And when you're erasing structures and making structures, what decides in the complex universe? Selection. So what is selection? Well, selection is the environment acting on that complex structure to say, hey, that's fine, you fit in my environment. I'm not going to dissolve you or kill you. It's an arbitrary thing, right? It just happens. It's a result of a physical interaction. And some things are erased and some things survive. And when they survive, they can survive by luck or by robustness, or if you can only get you can't get very far with luck and robustness. In the end, you just get dissolved, right? But if you become an active participant in the selection and you can learn from what the environment is about to do, you have cues, it's what's going to happen next, and you can get other stuff and make copies of you, suddenly you can outlive the environment, right? You propagate forward.
Right.
So selection is a natural phenomena.
Right.
Selection is as natural as gravity. If you bring stuff close together that's heterogeneous and interacts, you will get selection. It's as simple as that. So selection is symmetry breaking in between objects, creating structures that can then act on other structures that act on themselves. And you have this kind of loop of causation within time going forward to basically trap memories or information. It's when random events become causal and then become reproducible. That's selection. Right. And that's why we're here.
Right.
And it's kind of cool.
Yeah. I mean, I'm kind of imagining this exponential growth curve in, say, from my sort of computer science background, I would sort of say it in a sort of in an information level, but perhaps in an ability to get ahead of entropy, and that evolutionary biology on Earth is just a segment on that exponential growth curve. And there was some point. I mean, you can sort of take the same thing in terms of energy use, like right now, the humanity uses a certain amount of energy, and you can actually trace that exponential energy curve back to the beginning of humanity. You can even trace it before humanity when you think about other things and their ability to use energy, and it's this smooth exponential curve.
I mean, I think you're mislabeling some things, but what you're saying here is absolutely right. I think living universes die faster, right? They're able to just exploit resource, and what they do is they use that resource to generate novelty and basically go further than just the non-simple deterministic universe would be. But I would say that there are a couple of things that say the entropy is not, again, I think entropy is a fake term, but we should use it because when the observer uses entropy, it's useful. Okay, so I'm just saying that the entropy is not an inbuilt thing in the universe. Time is, and if you accept that, you don't need entropy.
Right.
Everything you get out of the mathematics of entropy happens in time. That's kind of like such an obvious thing. But chemists are taught entropy. We see how things work. Physicists love entropy because they need to do their bookkeeping. But there is this thing about understanding the resource use. The resource use is good. The other thing is that information theory doesn't really work here, because what we've got to try and do is information theory that physicists use was invented by an electrical engineer doing modern communications. And corrupted by Feynman and a load of other people, right? Great physicists can do no wrong, but they mislabeled things. And there's a series of mislabelings. And what I want to correct is the following notion. Selection produces the observer. The observer somehow also produces the receiver, or the encoding decoding system. When those are produced and they are talking to each other, then that can be called information.
Right.
But there was causation and selection before information. But when we start to mix up information from different domains and different labels, it all gets really messy, and it's a blind spot into our understanding of life. The reason why physicists do not understand life and computer scientists don't understand reality is they don't understand information in the substrate. And they'll argue with me. They're telling me off right now. I can hear it. I'm not pointing to a problem. All the problems I'm describing can be solved by a bigger computer and better labels and all this. But okay. I mean, I'm happy to have this argument over a couple of years, and I'm happy to hone it and say, this physical phenomena cannot be understood by our current understanding of physics, information theory, and computer science.
Right.
Therefore, we'll all have to suddenly believe in a non-material universe, or we can reinvent our understanding of the material universe to be predictive rather than just a history lesson. Right. Because what we're really bad at is predicting complex systems.
So, obviously, as computer scientists, we just want to know whether you can tell us whether P equals NP. But can you, practically, this idea of well, you know what? We could spend a long time here, and I would like to get to some of your practical ideas for searching for life.
You can ask this if you want, and we can keep it short. I promise. It's okay.
Well, just sort of. I guess I feel like you didn't really answer the question originally, which was if we've got this kind of selection pressure that's happening from the beginning of the universe, that biology is taking over and accelerating it, then it makes the existence of life feel like it's inevitable.
No, sorry, I did answer it, but maybe it could be. Yes, life is every universe. Life is with the current way the universe works, I would say life is inevitable as the birth of and death are a start.
Right. Okay.
Completely. Or rather, let's cite what I tried to say is let's not think about complex life, think about selection.
Yeah. Whether
selection is able to get to the end point, which is an alien civilization, intelligence, iPhones, it's just on a line connecting them. So to be concrete, I think selection is the thing that gives us life. How far you get depends upon how much time you have available and stuff.
Got it.
Is that a better answer?
Yeah, that's perfect. And so it does punt the question forward, where we could say, instead of where did life come from, we could say, where did selection pressure come from? Where did selection come from? But that's a whole other.
No, it's easy to answer.
Well, it's an outcome of the laws of physics themselves at this point.
Well, selection comes from heterogeneity in the universe. Mm-hmm. And where does heterogeneity come from? It comes from time. Right. And it comes from the fact there is broken symmetry in the universe. CPT, it comes from CPT.
Yeah.
That's it. I mean, we don't know why. There may be universes where CPT doesn't break symmetry and there's no life in it and there is no time.
Yeah. So what I want to do then is I reached out to you originally because you wrote a paper and there was a press release, and they didn't explain it too well, but I could see what was being proposed, and I thought it was really interesting. So you have an idea for a sort of Swiss Army knife of life detection experiments. Can you talk about this?
Yeah, so it comes back to this theory of assembly that I'll talk about in a moment. But basically, I'll tell you how I kind of invented it, and then because it's really interesting around the whole kind of origin of life, chemistry, and so on. a few years ago, I asked myself, how complex? Now, what do we mean by complex? How many features does a molecule need to have before that molecule cannot have just arisen by chance, right? That molecule is as unlikely as my iPhone to self-assemble. And I thought about this a lot. And what I realized is it doesn't have to have that many. And there's some good physical reasons for that. And it's a bit like, let's take it much more simply. If I take a coin and I flick that coin and I flick two heads in a row, you'd be like, oh, okay, well, lucky dude. I get 3, you'd be like, yeah, okay, fine. I get 6, and you're like, hang on. And I get 10, you're like, okay, there's something wrong here. When I get to 20, you say, you are cheating. That coin is weighted.
Yeah.
And then, and I'm like, yep, sure. And, I get to 60. So what I wanted to say is, like, when I'm looking at molecules being made, you should view it like exactly how many flicks of a coin can I get to get to a complex molecule? Because the more complex the molecule, so let's just say we get to some complex drugs, where they may say, let's have, say, 29 atoms in them. Once you get to, say, 29, 30 atoms, if there is a lack of symmetry and you can count the fragments, it can't have arisen by chance. So I went, that's cool. Is there a way I can measure how complex a molecule is? Is this a new measurement of molecular complexity? I then thought about it, and there's a technique that chemists use called mass spectrometry. And what we do basically is, if you view well, I'll just tell you what happens. Actually, you take the molecule and you weigh it, but in an electric field. And what you do as you weigh it, you can cut bits off by just hitting them with electrons, and bits fall off. And as the bits fall off, there is a natural fingerprint for it falling apart. It's a bit like if you take a really delicate hammer and you take a nice porcelain teapot and you go bang once, it might fall apart into characteristic fragments. If you took a massive sledgehammer and bang, it would go to sand, so you wouldn't know anything. But if you just tap it and it breaks,
right,
you'd be able to say, oh, okay, how complex was my piece of porcelain beforehand? This is exactly the technique we use. We thought, okay, you have a mass spectrometer that you can put anywhere. NASA's got mass spectrometers on Mars. It's had them fly through Enceladus. We're going to be sending them to Titan. And a mass spec can open up its nose, gather some molecules, hit the molecule. And if the molecule falls apart, and there's more than 15 fragments you can count, there's a very high probability you've just got 60 heads in a row. So what does that mean? Does that mean you're really lucky, or life form created it? So, and one thing I should add very quickly: when you're looking at that molecule, you're not looking at one. In the mass spec experiment, you need to have about 10,000 identical ones. So it's not just a one-off chance. There's always a chance you have one really complex molecule. If you have 10,000 identical iPhones, it's not a fluke. There was definitely Steve Jobs making them at one point.
Right. And so this idea that the more complex a molecule, the more likely it has been formed by life. That holds with carbon-based life here on Earth. Like what is the most complex non-life molecule?
So that's a really nice question. So basically, if you just took a load of just atoms and mixed them up in a pot and fired them up in a furnace, or did a thing called like the Miller-Urey experiment, you'd only find molecules with typically between, I don't know, it's an exponential decay, exponential increase in explosion of stuff, billions of molecules, but they'll all be relatively small. Let's say for the sake of argument, less than 20 atoms. Okay, and then after that you get an exponential decrease, because there's just no way although you can get more and more complex molecules, the mass gets spread out of a big combinatorial explosion. Right. So all possible signatures are there. So because there's individual molecules. So take it another way. If I took the molecule strychnine, which is a poison you find in mushrooms, and I was to look at the formula and look at the number of ways I could make that formula, obeying the laws of chemistry, I could fill the entire universe with a liquid, like water, with the same density.
Right.
But each molecule in that liquid would be different. but have the same formula. Think about this for a second. The entire freaking universe, liquid, all with the same molecular formula, but each molecule different. I mean, that just breaks your brain. You're like, wow, okay. So that's like, so that then shows you how big chemical space is. It's bigger than space.
Right.
I mean, it's just that's why the chemists are the true astronomers in the universe.
That's really interesting. I mean, I think the expectation is that you've got water and you've got aluminum oxide and you've got these, you know, again, like that's what, 4 atoms, 3 atoms. And yet if you mash together aluminum and oxygen and fill the universe, more interesting things might form from it. But if you can just take this method of the mass spectrometer and just be chopping up these chemicals, just statistically, you would know if you were looking at life or not.
Yeah.
Yeah.
And even if you're really super conservative, and you say, oh, no. My friend who's super lucky, he always gets 10 heads in a row. And I'm like, okay, 20, 30, 40, just pick your number. And that's what I suffered from a lot with the chemists who said, oh, no, there are certain molecules on Earth which are magic. They can just form, just because. And I think what it is, it shows a basic lack of understanding of probability in the way we teach chemistry and Bayesian statistics. No, okay, of course, not all molecules are equally probable. And of course, there are biases given by quantum mechanics, but still the space is very large.
It's interesting. I sort of see an analogy with the Large Hadron Collider, where they're looking for that 6 sigma detection. It's really the same thing. You're looking for a statistical 6 sigma or 4.2 if you're looking for other particles, but you're looking for whatever is the sigma that's to say, okay, statistically it is unlikely that anything but life formed this.
Exactly.
Yeah.
So you got that the nail on the head. You might like to know the reason I formulated the theory in this way was actually inspired by the way the standard model works. I took exactly the reasoning you just used to say, okay, there's this thing called the standard model. Standard model makes these predictions about what types of particle are possible.
Yeah.
Then we can knowing something about the physics of those, we can then work out how they form and make a model of them, actually make a physical model. Then we can then work out what energies we're likely to see them. So we've got our theory, we have our model, we build our experiment, we analyze and look for data where it's predicted. And if it works, we've made the particles. So here, my theory of life at the moment, because it's a moving target, is that processes that can produce complex molecules, okay, with a certain number of features are living or associated to a living infrastructure of some description. Now I can count the number of parts and say, how improbable was this? I make a simulation and then can now say, right, I'm going to go and build a robot, and the robot's going to do random chemistry in the lab, like it's doing. I've got one in the lab right now doing it.
Wow.
It randomly adds chemicals, boom, 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 boom. And then when it finds a bit of complexity, it goes, okay, follow. How many steps do I have to follow? If I can get to 15, I can say, hey, here's my candidate biology. Here's my new life form. So, and that's the idea. The idea is to use this method to not only find life elsewhere in the universe, but to make new life in the lab and to start to get people to argue. Because people can say, when I do this, that's not life. That's a robot in the lab doing random chemistry.
Yeah.
And I'll say, but look at selection that's going on. Look at the random inputs. Look at the outcome. Look at the mechanism. And we'll have an argument. Because right now, our standard model of chemistry and selection, people argue about. And so I have to get that mathematics right and have to bring computer scientists, physicists, chemists on board. But I think I have a working paradigm.
Yeah, that's really interesting. So, how big is your robot? Would it fit on a Mars rover?
So the robot to make life stays squarely in the lab. It's pretty large. But the mass spectrometer, there's already mass specs on Mars right now.
Sure, but I'm assuming that you're tuning a mass spectrometer to be able to do this kind of bulk operation. It's going to require a little extra mass.
Yeah, it does. So there's good news and bad news. The good news is there's mass specs all over the solar system, thanks to NASA, and they can give us preliminary data. The bad news is they're not sensitive enough to have the correct resolution. But the next generation of missions, it will be easy to put on, well, easy, not easy, but it is physically within the realm of missions. Not in fact, they're already planned, right? I was speaking to NASA's chief scientist just a few days ago. We've had many conversations about this. NASA are now bought into this lock, stock, and barrel, and they're going to be hopefully putting this on, all the missions that I can see, because it doesn't cost them anything more. It requires them to basically think about their mass spec design. So as you correctly suggested, right now, the mass spec is like what I would call a single mass spec detector, whereas here you need to basically do a fancy thing. You need to detect your molecule, and then you need to hold that molecule or the bunch of molecules and then bash them and detect them. And that's called a tandem mass spectrometer. So you need to do mass spec. But there's what we call Orbitrap. That's the name of the technique or the name of the type of sensor. There are Orbitrap mass specs being built at Goddard Space Flight Center right now that are being hopefully going to be commissioned for flight.
Wow. Okay. So then I'm sort of thinking about a couple of like life equivalents of doing a core sample. So we know that on the moon, for example, the moon seems to store a record of the history of the universe in the regolith, all of the cosmological events, nearby gamma ray bursts, as well as material that's fallen off the sun, etc., just layered into the regolith. And I wonder, could you like take a core sample of the moon all the way back to 4.3 billion years ago, and then churn through that with your system to sort of see if there's any complexity increasing through that system?
So I think that's a very, very smart question for a number of reasons. I mean, first of all, we wouldn't use a mass spec, but let's talk about minerals. Minerals do exactly the same thing as molecules. As you add in more constraints, there is evidence of interesting things happening. In fact, life probably got started because in organic world, the minerals interact with the organic world and they got complex together and one seeded the other. And it's this kind of dance of selection. So minerals are at the core of this. And I think, the moon is probably pretty boring inorganically, but we don't know. We haven't gone all the way to the center. I'm sure there's surprises. So I think that we can apply this technique, not just using mass spec, but one thing I should add, there is also another technique that we can use that works called infrared spectroscopy. And we might even be able to do remote sensing of exoplanets to look at the infrared spectrum around the planets and pull this out. But this is maybe we can discuss this in a moment.
Yeah, that was going to be the next, well, actually the second to next line.
Well, we can come back to the minute. So answer your question. So what we're doing on Earth right now is we're trying to get lots of different mineral samples, and we're looking at the crystallography. So the crystallography allows you to basically look at the regularity of the lattice, basically by shining X-rays. You then know the elemental analysis, you know the elements in there. And what we're trying to do is look at the kind of the structures of the minerals. And also there are some minerals and some materials where they have defects. It's almost like you should view a defect in diamond a bit like storing a 1 or a 0 in a hard disk. So, the first genetic code is a random mess on a mineral somewhere, and that random set of defects imprints itself on the chemical mess, and that chemical mess peels off and then has causal consequences. Right. That's really how selection starts. People say, okay, you're talking about selection. What is a physical problem? Well, you have a surface with defects, fill it in with organics. Organics peel off. They have different shapes, and they go off and then do stuff in solution.
But the moon was sort of an idea as a fairly pristine place. But even here on Earth, I'm assuming you could find the oldest places on Earth, somewhere here in Quebec, in Canada, do a core sample again and slice it into micron layers and sample each layer and see if there's a story unfolding in the complexity of the minerals and maybe even the organics that are being deposited alongside the minerals.
When you do that, though, you need to be objective. So the problem with that is when you take a sample and you look optically and you count, you've got to decide what your basis set is. So what I mean by that, many people have mislabeled, or not mislabeled, they have found micro features, which they say causally could be a fossil. And that there was famous that meteorite that Bill Clinton went out and said they found life. That's why NASA have been a bit shy, because you've got the Viking mission found life, the meteorite found life, phosphine on Venus found life. Are they life? Well, I'm not going to get into whether they all found life or not, but the phosphine on Venus, interesting if proven, but very simple molecule. So lots of ways to make phosphine if you're an organic chemist.
Mm-hmm.
The authors of that paper argue that not there. Okay, fine. Then let's go to the meteorite, the fossil. Well, is it really a fossil, or is it just basically a random growth? And on the Viking mission, was it just a chemical artifact? And that's why by looking for these features, the 4 sigma, 5 sigma, 6 sigma allows you to really get in that. So what we have to do with the inorganic minerals is actually probe the elemental composition and the crystallographic composition and not worry too much about the optical micrographs, because otherwise you'll start fooling yourself, because you can see, like pictures in the human eye is very good at seeing pictures in things where isn't anything there, and you need to correctly weight that against the abundance. If, however, you opened up 2 minerals and let's say you found your face, it's like, there's a picture of me in this mineral. Wow, that's weird, but that's a one-off.
Right.
Then you open up another one, there's you again. You're like, oh my God, I have, many million features. I'm a complicated individual. Look at me. And look, there's another one exactly the same. And again, you keep doing it. The only thing you conclude is there's some alien artist somewhere who predicted you, painted you in a rock and left it on the ground for you to come and find it.
Right.
I mean, that would be the only conclusion, right? If you found many rocks in abundance with exactly the same features. That's the trick.
Yeah.
So you have to define that feature space correctly.
So there's this idea of a shadow biosphere. That life has actually evolved multiple times, and it's just not the dominant life form, but it's still eking out some kind of existence living around the margins of life as we know it. Do you think that there would be a way to determine this using your methods?
Yes. And so right now what we're doing is that so the reason why I think yes, right now there's lots of stuff on Earth, and we're generally, because molecular biology is becoming more and more and more technical, using the technology we have associated with biology, so understanding RNA and DNA, how we get into sequences. If there's stuff that you can't culture or can't sequence, you are going to ignore it. You're not going to count it. But the nice thing about this method is it doesn't ignore that. It basically allows you to see all the molecules present. So what we're doing right now is we're taking representative examples of bacteria and living things from all around the kind of the tree of life on Earth and the location, and we're fingerprinting it in terms of molecules and their assembly number. So what does that mean? So we're taking some E. coli and we're looking at the molecules present and then counting out how complex they are, making a 2D grid. Then we're maybe taking another bacterial sample and doing the same thing. And because each sample will have its own fingerprint, and there'll be common molecules, because common molecules in life, you'll get this kind of pattern in molecular space. Then, so we're going to say, right, that's what we think biology looks like. Then we'll go and look more broadly and try and find outliers that are complex, but don't seem to fit in this pattern. And then we're going to say, hang on, is this an alien in plain sight? And dig down. And I think I don't really think that I really have a very firm opinion on the likelihood of finding a shadow biosphere. On some days when I think that Earth really, the transition to biology was a planetary phenomena, and there was differentiation at the beginning, but we then coincided. Biological democracy, I call it, or pre-biological democracy that Luca, right, dominates. So we've all adopted one chemistry because it's so fundamental. But then other days I think, well, maybe some of that pre-biotic Luca got trapped somewhere really deep and was isolated for long enough, there's a chance. But the problem is that isolation. We're finding that life gets everywhere on Earth. There is no hermetically sealed containers.
Right.
Life
finds a way.
There are no obelisks.
Yeah.
So but that doesn't mean there hasn't been a shadow biosphere that we just haven't noticed yet, and there's something else going on. So let's look for it.
Yeah, but I like this idea of going at it statistically. It feels like such a wonderful way to do this. So you sort of mentioned it, but now let's dig into this. How can we use this technique with our space telescopes to look even here in the solar system? I mean, Venus is the perfect spot with this announcement of phosphine, but how can we scale up and examine the atmospheres of other planets across the Milky Way for any kind of evidence?
So I mean, the short answer is really hard because of resolution, but let's just pretend for a second that we had, a telescope the size of the solar system,
Okay.
and that we could basically, get return spectroscopy, right? So that, where we could shine a light on something and the light could come back, and it'd be simple-ish, right? There's no science fiction there. It's just hard. So a number of things you can do. First of all, is that assembly theory doesn't just talk about the number of features in the molecule. Each bond you put in a molecule, you can think about a reaction occurring to do that. So you could, rather than just thinking in what I would call Cartesian space, you can think in frequency space. So basically, there are reactions occurring rapidly to make that molecule, lots and lots of reactions. They have a characteristic frequency or rate constant. So what does that mean? If in an atmosphere you saw lots of gases changing the concentrations, and you could actually collect enough data in the infrared and see that as the concentrations changed, there was a relationship between all of them. If you were able to find a system that had 15 more independent variables controlling the bunch or more, I would probably say, well, hang on, there is something really weird going on. Mm-hmm. It wouldn't be as diagnostic as finding it in a single molecule, because a single molecule has all that information compressed at the nanoscale, whereas here you're integrating over an entire planet. That's the kind of short-term view that you might be able to do. But let's now pretend that I have a laser.
Sure.
And I fire the laser.
I mean, they're going to build 1 million lasers for Starshot anyway. So they'll build this laser array. Yeah, so they'll build this laser array. Yeah, and you'll use it to blast Alpha Centauri.
Yeah, so what we then do is there's a thing called infrared fluorescence, or a technique that I made it up, right? Sorry, I'll start again. I could imagine an experiment where I would, so here's a problem. Let's just say I've got a mixture of gases. I do infrared. In my infrared spectrum, I'm going to see a mixture of gases. It's like, so I need to do a thing called chromatography. Now, normally the way chemists do chromatography is they get some filter paper or stationary material and they move it through with a solvent or gas, and then it separates. Well, we don't have that. I can't gather up all the molecules. Well, what I could do is I can do some time-resolved spectroscopy where I just say I take a laser pulse and I fire the laser. Let's say I can control it down to a femtosecond. So, boom, given molecule in a plume, all the identical molecules absorb that light. Then the energy gets dissipated through the molecule, and then they give off a characteristic glow. Because I knew how long ago I sent the pulse, and then I can count the time it takes to come back. I can collect the infrared coming back from that molecule and that molecule alone and work out how many bands there are. It's not infeasible you could do that, but it's a hard experiment.
I mean, it sounds like radar versus radio in terms of doing your astronomy, which is...
You do this type of experiment with NMR right now, nuclear magnetic resonance. In the laboratory, what you do is you put molecules in a magnetic field, you hit them with radio frequency, and then you measure the radio frequency coming out. So this is a bit more diagnostic. So the radio frequency reads out the different nuclei present, the different spin, magnetic spin from the nucleus. Whereas in this experiment, you would just measure the number of different bonds. So it's a fluorescent infrared experiment. Right. The reason I want to do it fluorescently is it allows me to get time resolution, so I can pick one particular type of molecule out. But there might be good reasons why I'm going to be confounded there. But in general, if we were able, let's just say we were advanced alien civilization. Well, let's just say I can tell you what I would do if I wanted to leave a calling card on Earth. Let's say I'm the last person alive on Earth, and I want to tell aliens I was here. What I would do is I would go to my lab quickly, and I'd make a highly volatile gas, as volatile as possible, 1 million tons of it, and I would put as many different bonds in there, fluorine, chlorine, bromine, iodine, in a sequence, and I'd write a little message in the molecule, and I'd put it in the atmosphere. Because then when they shine an infrared laser on the Earth, they would get so many lines in one molecule, they'd be like, holy cow. Right. This is like, someone is saying there is a complex molecule in the atmosphere that could not have been produced by natural processes because there's so many weird bonds in the one molecule.
I wonder if there's a natural source that could get you what you need, because building a 1 million laser array, blasting Alpha Centauri, having a telescope the size of the solar system to receive the signal seems hard. But, if there's some event, a pulsar nearby, a gamma ray burst that's going to illuminate the atmosphere, something, a flare, from a star that's going to randomly, at a very predictable way, change the atmosphere of the star. I wonder if there's a way you could find some natural event that would get you what you need.
I think so, but I think that the best way is to go a bit more statistically and not demand the same level of statistical scrutiny that we can get in the solar system from mass spec. So what do I mean? Let's just say we're getting more and more familiar now with the concept there are exoplanets everywhere. And there's only 4 types of exoplanets I can think of from the top of my head. There are ones that are dead, okay, that never ever come alive. Let's just say, or they're dead at the moment of observation. Let's not prejudge your future because Elon Musk hasn't got there yet. There are ones that are alive, but no technology. There are ones that are now not only alive, but they're technological. In fact, they may be post-life. But for all intents and purposes, we should call them alive because, what's the difference between technology and life is hard. And then there's a final category. There was ones that were living, but now they've died. They were artifacts. So you think about it, there's only 4 types of exoplanets in the universe. Let's observe all the exoplanets and see, are there 4 signatures? Can we statistically put people, can we bin them into A, B, C, or D?
Yeah.
Right? And just occasionally, if they're in C, do aliens come from them and try and blow us up or communicate with us?
Right.
Because we can see everywhere in the universe, and we've got the transit method, and it's mind-blowing to consider that we see these exoplanets. There's going to be life on some of them. That's a conjecture.
Yeah.
So let's pretend there is and see and categorize them. What other features can we see? It might be that exoplanets in general, there's one particular type of exoplanet that looks weird, seems to have lots of little things around it, dust cloud. We might call them satellites. So there's all sorts of ways of doing it. But we have to think, the message I'm giving you very strongly is we have to think statistically.
Yes.
And we have to look for information, and we have to look for we have to think probabilistically in assigning the priority to that information.
It's interesting, like right now we know of 3,000 confirmed exoplanets, thousands more unconfirmed. But if you graph that exponential curve, I think it hits about 100 million by 2050. So we'll know of a lot of planets, and then the full weight of statistical analysis will be able to come to bear at that point. We won't talk about individual planets anymore. We'll talk about these classifications. One more idea for you is that the Milky Way does seem to be sending some of these samples our way. In the case of, say, Oumuamua and Borisov, these interstellar comets, and it's believed there's probably tens of thousands within the solar system at any time, multiple ones within the inner solar system at any time. Would getting your hands on a sample of one of these interstellar objects be helpful?
I would love to, right? I mean, what we should do, if you're thinking about it, the objects aren't only coming through us; we are moving through the objects, right? So it's a relative. But yeah, I mean, if we had detection systems all over the solar system, mass specs, infrared spectrometers, and we're able to audit the stuff that's coming through, we might be able to tell the difference between something that was naturally occurring and something that was created either by a technology or by evolution, just by having an idea of the abundance of the object or the sub-objects within that mass and the number of degrees of freedom that were involved in producing those features. So it's a bit like what you're doing is you're looking for not just, think of your favorite artist, maybe a painter or a sculptor. You're not looking at one object from them, but you want to find 10,000 and you want to be able to statistically kind of go, this, I don't know, Monet or Jeff Koons or whatever has been here again, right? Because they're making copies, but they're complex copies. And I think that's a super interesting way of looking at life in the universe.
It sounds like sort of the same technique again and again, that you're looking for some way to analyze it statistically, whether you've got one little blob of material that you're examining in the lab, or you're examining all of the planets in the Milky Way that you can get your hands on. The same underlying methodology comes to play. It's just which experiment you're performing is slightly different. Yeah.
I mean, my major conjecture is that that complex objects that have a number of facets, have a number of features that you can't explain if they have an abundance with from a natural process. have to have gone through a process of selection. And I think that's going to become more and more obvious, because what I'm saying is like, there is one force in the universe that we haven't accounted for yet. Well, there's probably many, but this force is selection. Now, selection is not necessarily a physical force, an attractive force. Selection is an information force or a causal force. Selection gives causation in the universe. Before selection, there is no causation. I think that's the most profound thing I can say here. Without selection, there is just a universe of things bumping into one another. As soon as you get selection, there's something weird that happens to space-time. And we haven't yet got our heads around that. And the average physicists say, no, that's just nonsense. But well, I think that the data, as I say, in my experimental theory, I'm looking at this data and saying, hey, there's something going on here that the theoreticians, the real theoreticians, as it were, cannot really account for. So that is exciting, because that means there's a mystery, and I love mysteries.
Do you think that it allows predictive, you to make sort of predictive guesses about what the future holds?
I think so. I think that selection selection does boring things, right? As well. I actually produce very low complexity molecules right now. I'm breathing out CO2. But what life seems to be doing, and technology seems to do, is search more and more for novelty in the state space, right? More and more unusual things. So I think that predictively would say you really want to look for processes that are highly anomalous. So you almost want an anomaly detection system on your telescope, as well as a, categorical tool.
Very cool. Lee, thank you so much for taking the time to chat with me today. This was really fascinating. If people want to follow your work and keep track of your discoveries, where should they go?
They could go to my website, croninlab.com, CRONIN lab.com. Look at me on Twitter at Lee Cronin, and then just generally follow on the web as things are happening.
All right. Well, and if you do discover life in the universe, let us know.
I'm working on it. I'm not sure we're alive yet, but we're getting there.
All right. Sounds
really
great.
Nice to talk to you, Fraser.
Thank you so much. Take care.
Yeah. Okay, we're now off the air.
1 second.